Welcome back to the deep dive. You've brought us some really dense and fascinating material today. It feels like we're pushing right up against the fundamental boundaries of reality itself.
We really are.
We're tackling a question that, well, it seems simple on the surface, maybe, but it contains just centuries of philosophical struggle. It's this. Does the number 7 exist? Like, really exist in the same objective, durable way that a star or an atom exists?
It's a profound question, and it's the ultimate metaphysical puzzle for anyone who uses or thinks about mathematics, really. We talk about numbers, sets, functions. We treat them as objective, eternal truths, things that are just completely indifferent to human existence.
Right.
But, if there are objective truths, then where do these truths and the entities they describe? Where do they actually reside? Are they floating around in some kind of, I don't know, ethereal realm? Or are they just inventions, things we've made up in our minds?
And the specific answer we're diving into today is mathematical Platonism. Now, we hear Platonism used quite a bit, but our sources, they define it very rigorously, don't they?
They do, yes. It's quite specific. Mathematical Platonism is a particular metaphysical account, and it asserts three core things, three foundational theses about mathematical entities. Numbers, sets, geometric shapes, whatever.
Okay, what are they?
First, they exist. Simple enough, right? They have being. Second, they are abstract, which means non-spatiotemporal and a causal. We'll need to unpack that.
Definitely.
And third, they are independent. So their existence, their properties, they're entirely independent of human minds, human activities, anything like that.
Okay, so if I think about, say, a perfect geometric sphere, if I accept that its fundamental properties existed before any person ever thought about geometry, then I'm sort of leaning Platonist. That sphere is just out there, fully formed, completely separate from me.
That's exactly the idea. The Platonist argues that the objectivity we see in math, the fact that 1 + 1 = 2, is just true for everyone, everywhere, always.
Yeah, it feels bedrock true.
Right. And the best explanation for why it's so bedrock true, the Platonist says, is that there's this independent, abstract subject matter that math is about. In fact, many people sort of see Platonism as the default position, metaphysically speaking.
Really? Why is that?
Well, because it seems to take the everyday practice of mathematics, just literally. When a mathematician proves a theorem and says there exists an infinite number of prime numbers, the Platonist just nods and says, yep, that object, that infinite set of primes, it exists outside space and time.
Okay, let's really unpack this then. Our mission for this deep dive seems to be threefold. First, we need to properly define those three crucial theses: existence, abstractness, and independence. Get really clear on what they mean.
The foundations.
Second, we need to trace how this, pretty ambitious view was systematically defended. How did philosophers try to prove it? We'll look at Frege's logic and then this Quine-Putnam indispensability argument, which sounds important.
Very important, yes. It shifts the focus to science.
And finally, we absolutely have to confront the central, maybe terrifying challenge to Platonism, this idea of an impenetrable metaphysical gap that seems to separate us from this abstract realm.
Yeah, that's the kicker. Because if these mathematical things are truly a causal and non-spatiotemporal, well, that gap creates some devastating problems. Problems for how we could possibly know anything about them.
It sounds like a real philosophical tightrope walk.
It is. It's a spectacular balancing act, and we need to really understand how Platonists try to stay on that rope, how they try to maintain their position against these challenges.
Okay, let's start by laying the groundwork, beginning with the simplest but maybe the most profound claim, the existence thesis.
Right. This is just the core claim that something mathematical exists, some mathematical ontology. It's the heart of mathematical realism.
Ontology meaning?
The stuff that is. Exactly. Whether that stuff consists of objects like the number 2 or maybe structures like the whole system of real numbers. The point is something external to us has being. It exists.
Okay. Simple enough to state, maybe harder to defend. Now, let's move to the abstractness thesis. This seems to need careful handling. When a philosopher says abstract, they don't just mean like theoretical or hard to grasp.
No, it's a technical term, really, a term of art. It's best understood by contrasting abstract things with, concrete things.
Right.
Concrete objects, planets, rocks, brains, electrons, they're spatiotemporal. They have a location in space and time. They have mass, maybe. And crucially, they participate in cause and effect relationships.
Okay.
Abstract entities, on the other hand, are defined precisely by lacking these features. Our sources describe abstract as a a cluster concept.
A cluster concept.
Meaning, an entity is considered abstract if it possesses a bunch of defining features from a specific list or cluster. There's not always one single necessary condition, but there are definitely core features. And for mathematical Platonism, two features are absolutely central.
Okay, let's hear them. What's the most central one?
That would be non-spatiotemporality. The entity simply doesn't stand in relations that would make it a part of the spatiotemporal world we inhabit.
How do we get our heads around that?
Well, you try and you fail to locate the entity in space or time. It's almost a diagnostic test. I mean, try it. Where precisely is the number 4?
Nowhere. I mean, I can write the numeral 4 on a piece of paper, but that's just a symbol, right? Not the number itself.
Exactly. The numeral is concrete, spatiotemporal. The number 4 itself, where is it?
I can't point to it. And I guess I can't say it's just in my head either, because the Platonist insists it's independent of my thinking about it.
Correct. It's not a mental object. And that's why questions like, how much does the empty set weigh? Or what's the velocity of the Pythagorean theorem? They sound absurd.
Yeah, they're category mistakes, like you said.
Because the entity fundamentally lacks the properties needed to participate in space and time. It's nowhere and no when, so to speak. It doesn't have mass or velocity.
Okay. Non-spatiotemporal. Got it. What's the second crucial feature in this abstractness cluster? You said it sets up problems later.
Yes, this is a causality. And it really is the one that causes the major philosophical headaches down the line.
Okay. What does acausality mean here?
It means mathematical entities neither exert nor receive strict causal influence. Now, we have to be a bit careful with strict causality here.
How so?
Well, of course, the idea of a number, like the idea of building a bridge according to certain calculations, can cause a person to act, to actually build the bridge. That's psychological causation.
Right. My belief about numbers has effects.
Yes, your belief, a mental state, is part of the causal world. But the abstract number itself, the number 2, say, is causally inert. Think about it. If I kick a football, my foot causally influences the ball. There's a physical interaction.
Sure.
But you cannot, in any way, shape, or form, kick the number 2. You can't affect it. You can't affect you, not directly. It's causally sterile.
So I could, scribble the symbol 2 on a piece of paper and then burn the paper. But the actual abstract thing that is the number 2 remains completely untouched by my little bonfire.
Precisely. It's utterly unaffected. So if we accept these two big ones, non-spatiotemporality and acausality, the Platonist usually adds about 4 other features to this cluster. These really solidify why mathematical entities are seen as paradigm cases of abstractness.
Okay, so there's an abstractness plus thesis almost. What are these other 4?
Well, first there's eternality. If something isn't in space and time, its existence can't really be bounded by time, can it?
Suppose not.
So it's considered either omnitemporal, meaning it exists at all times, past, present, future, or maybe even atemporal, meaning it exists completely outside the framework of time altogether.
Outside time. That's hard to grasp.
It is. And this leads naturally to the next feature, changelessness. If something is atemporal, outside time, how could it change? Change usually implies having one property at one time and a different property at another time.
Right. No time, no before and after for properties to change.
Exactly. So its intrinsic properties cannot change.
Yeah.
The number 2 can't suddenly wake up and decide it wants to have the properties of the number 3.
Okay, but just push on that a bit. Why is changelessness philosophically necessary? Couldn't a non-spatiotemporal thing still somehow evolve or shift internally?
It's a good question, but think about how we usually define change. It involves time, right? Property P at time T1, lack of P at T2. If the entity is literally outside of time, that definition just doesn't get any traction.
Okay.
And even if it's just omnitemporal, existing at all times, the idea that its core identity could just spontaneously shift without any external cause because it's a causal, well, that becomes very difficult to make sense of. Change seems to require either interaction or time, and Platonism rejects both for these entities.
That makes sense. A causality blocks internal change, too, in a way. Okay, 2 more features.
Fifth is necessary existence. The idea here is that the entity couldn't have failed to exist. Mathematical truths like 2 + 2, 4 feel necessary. They aren't just true in our world. They seem true in all possible worlds.
Unlike, say, the law of gravity, which we could imagine being different in another universe.
Exactly. You can imagine a possible world with different physical laws, maybe gravity works inversely cubed, whatever. But can you coherently imagine a possible world where 2 + 225 is true?
No, that feels like a contradiction in terms.
Right. And if the truths of arithmetic are necessary, the Platonist argues, then the objects that make those truths true must also exist necessarily. Their existence isn't contingent, it's required.
Wow. That is a really demanding picture of what these things are. Okay, and the final foundational thesis, number 3.
That's the independence thesis, and this is where Platonism really distinguishes itself from other views, like constructivism.
How so?
It simply states that the mathematical ontology, the objects, the structures, whatever they are, would exist even if there were no rational beings at all. No minds, no mathematicians, no activity.
So the Pythagorean theorem was true before Pythagoras, before humans, before any minds existed.
Yes. And furthermore, those entities and truths would retain all their features even if our rational activities, our ways of thinking or doing math, were different.
So even if we'd evolved with a completely different language or system of logic, 1 + 1 would still equal 2 in the Platonic realm.
That's the claim. This independence thesis is really the philosophical muscle behind the idea of mathematical objectivity.
Right.
The Platonist says, look, mathematics is incredibly objective, precise. It works amazingly well to describe the physical world. How do we explain that? The best explanation, they argue, is that math has a subject matter that exists entirely independently of us and our activities.
And without that independence?
Well, mathematics starts to look like maybe just a human game or sociology or psychology. It risks losing that hard objective edge that seems so central to it. Independence grounds the objectivity.
Okay, so we have this really robust, quite demanding definition. Existence, abstractness, with all its facets like a causality and necessity and independence. But, philosophical claims, especially big metaphysical ones like this, need more than just definition. They need systematic defense.
Absolutely. You can't just state it. You have to argue for it.
So we turn now to 2 really monumental arguments that philosophers have developed to try and demonstrate that Platonism is actually true. The first one comes from Gottlob Frege, a huge name in logic and philosophy of language.
Indeed. Frege was working late 19th, early 20th century, and he was deeply concerned with the foundations of arithmetic. He wanted to show it could all be derived from pure logic. And part of that project involved getting really clear about the difference between objects and concepts, and he used language as his guide, his diagnostic tool.
Okay.
So his argument for what we now call object Platonism, the view that mathematical objects like numbers exist, is often called the semantic argument, because it relies heavily on how we use language when we talk about numbers.
Okay, let's walk through that Phrygian logic. You said it starts with simple, true statements.
Yes. Step 1. Frege observes that singular terms, which function grammatically, like proper names referring to natural numbers, appear in statements that we take to be true. Your earlier example was perfect. The number of states in the USA is 50.
Okay, and 50 there is the singular term.
Exactly.
Yeah.
It functions like a name referring to a specific thing.
Yeah.
The number 50. That's the linguistic data.
Right. Step 2 then.
Step 2 is the crucial semantic inference. Frege argues that for a simple statement containing a singular term to be true, the object referred to by that singular term must exist.
Can you give an example of how that works for falsity?
Sure. Think of the statement, Sherlock Holmes lives on Baker Street. We'd say that's false, right? Why? Primarily because the singular term, Sherlock Holmes, fails to refer to any actually existing person.
Okay, makes sense.
But now take our true statement. The number of states is 50. If this statement is true, Frege argues, then the singular term 50 must successfully refer to an existing object. That object is the number 50.
Ah, I see. The truth of the statement guarantees the existence of the referent.
That's the core move. And just like that, based on how we use language, Frege believes he's established the existence thesis, at least for the objects of arithmetic, the natural numbers.
Wow, okay. But that's just existence. How does he get to abstractness and independence from there?
Well, once existence is established via language, he layers on the other observations. Step 3. He argues that these numbers we've just shown exist are clearly not physical objects. They don't have mass or location.
Right.
And they're not purely mental objects either, because mathematical truths are objective, not just subjective opinions. So they must be abstract. That's the abstractness thesis. And step 4. He observes that arithmetic truths seem objective and necessary true, regardless of what anyone thinks. This points to the independence thesis. Put it all together, Frege concludes, an arithmetic object Platonism is true. It's a really elegant, clean argument based on semantics.
It really is. It flows very logically. But you mentioned earlier this runs into a serious problem, a scale problem, when we try to move beyond basic arithmetic, beyond the natural numbers. why does Frege's reliance on singular terms start to break down?
Yeah, this is a major issue. It comes down to the limitations of, well, human language and finite minds. Frege's argument works beautifully for countable sets, like the natural numbers, 1, 2, 3, and so on.
Why countable?
Because our natural language, or at least the formal systems that we can build, contain procedures algorithms, essentially for generating a unique singular term, a name, for any natural number you want, no matter how big.
We can always just keep adding +1 and generate a name for the result, even if it gets incredibly long.
Exactly. There's a system for naming them all, in principle. But now, consider the real numbers. That's the set of all numbers in the continuous number line, including all the integers, all the fractions, and all the irrational numbers like pi and the square root of 2.
Okay, the continuum.
Right. And the crucial mathematical fact here is that the set of real numbers is uncountable. It represents a higher order of infinity than the natural numbers. You literally cannot put them in a one-to-one list with the natural numbers.
I remember Cantor's diagonal argument proved that.
Precisely. And here's the problem for Frege. There is simply no way for any natural language, spoken and understood by finite human beings, to contain a unique, singular term, a unique name for every single real number. There are just too many of them, infinitely more than we could ever name.
Okay. So if Frege's argument hinges on a singular term appearing in a true statement,
Right.
and we literally cannot form singular terms for the vast majority of real numbers,
then the argument fails to establish their existence. If Platonism is supposed to be a general philosophy covering all of mathematics, including calculus, analysis, set theory, which all heavily rely on the uncountable real numbers and other large infinities, then Frege's argument, based on naming, just doesn't scale up.
it leaves out most of modern mathematics.
It does. It became clear that if Platonism was going to survive and cover the full scope of math, it needed a different criterion for ontological commitment, something that didn't depend on the accident of whether we finite humans could name every entity.
So the focus had to shift.
Exactly. The focus shifted away from individual names, singular terms, and towards something more general, quantification. What sorts of things are we implicitly committing ourselves to when we state broad scientific laws or mathematical theories? What do our theories quantify over?
And this shift, this is what brings us to the second major defense of Platonism, the Quine-Putnam indispensability argument, or QPIA.
Precisely. This argument really dominates the discussion in modern analytic philosophy, and it takes a completely different tack. It shifts the justification for believing in mathematical entities away from pure logic and language analysis and towards the authority of our best empirical science.
Okay, that sounds like a big move. What are the underlying principles? You mentioned 2 guiding ideas.
Yes, the QPIA operates under 2 very strong philosophical commitments. The first is naturalism. This is the view that science is our best, maybe our only, reliable guide to reality. There's no special first philosophy or armchair metaphysics that stands above or outside of science and tells us what really exists. If you want to know what exists, you look at what our best scientific theories need to assume exists.
So philosophy follows science, not the other way around.
In this view, yes. And the second principle is confirmational holism. This is the idea, most famously associated with Quine, that scientific theories are not tested or confirmed statement by statement in isolation.
How are they confirmed then?
They face the tribunal of sense experience, as Quine put it, as a whole corporate body. When we perform an experiment that supports, say, general relativity, we're not just confirming one equation, we're confirming the whole theoretical package, the laws, the auxiliary hypotheses, and crucially, the mathematics that's woven into the very fabric of that theory.
Okay, so the success of the overall scientific theory lends support to all its essential components.
That's the idea. The confirmation spreads across the whole system. If a part is truly indispensable to the theory's success, then the evidence for the theory is also evidence for that part.
So if I, launch a satellite and it orbits exactly as predicted by Newtonian mechanics plus some relativistic corrections,
Yes.
I haven't just confirmed the physics laws, I've also implicitly confirmed the existence or validity of the differential equations, the real numbers, the vector spaces, all the math that was necessary for those predictions.
That is the absolute core of the Quine-Putnam indispensability argument. It unfolds in basically 3 steps. Step 1. We ought to have ontological commitment to all entities that are indispensable to our best scientific theories. This comes straight from naturalism and holism.
Ontological commitment meaning we should believe they exist.
Yes, we should accept them as part of our inventory of what is real. Step 2. Mathematical objects or structures are indispensable to our best scientific theories, like physics, chemistry, biology, etc.
You can't do physics without math.
You really can't, not advanced physics anyway. Step 3. Therefore, the conclusion follows. We ought to be ontologically committed to mathematical objects or structures. We should believe they exist.
That seems incredibly powerful. If science needs math and we trust science, we have to trust math exists. But that word indispensable seems to be doing a lot of work. Surely science uses helpful models or fictions sometimes that aren't really real. How strict is indispensable?
That's a crucial point, and Quine was very precise about this. He provided a technical criterion of ontological commitment. It's not just about convenience, it's about logical necessity within the theory itself.
Okay, what's the criterion?
Quine argued that we are ontologically committed to exactly those entities that must be counted as the values of the bound variables, the things our quantifiers range over, in the optimal formal representation of our best scientific theory.
Whoa, okay. Bound variables. Optimal formal representation. Let's unpack that. What does optimally formulated mean? You mentioned Quine called it canonical notation or regimented language.
Think of it as translating the scientific theory from potentially fuzzy natural language into the rigor of formal first-order logic. You strip away all the metaphors, the ambiguity, the shortcuts, and you express the core claims of the theory with maximum logical clarity.
Like cleaning up the language.
Exactly. And once you have this cleaned up, logically precise version, you ask, does this theory, in order to be stated truly, require us to use quantifiers like there exists some x such that? Where the x refers to a mathematical entity, like a number, a set, a function, or a space.
Can you give an example of how this regimentation works? You mentioned one in the sources about a possible job.
Right. In casual talk, I might say, I sought a possible job for you today. That sounds like I'm committed to the existence of this abstract entity, a possible job.
Yeah, it does.
But when we regiment that into canonical notation, trying to be precise, we might translate it as something like, there exists a job advertisement, a concrete thing, ink on paper or pixels on screen, such that the position described in that advertisement might be suitable for you.
Ah, okay. The reference to the abstract possibility disappear.
Exactly. The ontological commitment shifts. We're now only quantifying over the concrete advertisement and maybe the abstract concept of suitability, but not a free-floating possible job.
Okay, so the crucial step for the Platonist using QPIA is to show that when we take our best scientific theories, like quantum field theory or general relativity, and we regiment them into this rigorous logical language.
Yes.
The variables that represent mathematical entities, numbers, fields, spaces, sets, they still have to be quantified over. We can't paraphrase them away like a possible job.
That's the claim. The argument is that you simply cannot state the laws of physics, for instance, in their most precise and powerful form without quantifying over mathematical entities. They are inescapable if the theory is to be expressed and function correctly.
And if we're forced to quantify over them in our best science,
then, according to QPIA, driven by naturalism and holism, we are forced to accept their existence. We are ontologically committed.
And does this also support abstractness and independence?
Implicitly, yes.
Yeah.
Because the way mathematics functions within science treats it as objective, necessary, and independent of the observer. Science uses math as if Platonism were true. So the argument goes, the commitment derived from science carries with it these Platonistic features.
And crucially, this QPIA approach, focusing on quantification rather than naming.
It completely overcomes Frege's scale problem. It doesn't matter if we can name every real number. What matters is whether our theories need to quantify over the set of real numbers or functions defined on them, and science clearly does. So QPIA can defend the existence of uncountable domains, structures, anything that science indispensably quantifies over. It's much broader than Frege's argument.
Okay, so if we accept the force of the QPIA, we find ourselves ontologically committed to, well, some kind of mathematical entity or entities. But that leaves a pretty big question open, doesn't it? What kind of entity are we actually committed to?
Exactly. The QPIA gets us to existence, but it doesn't necessarily specify the nature of that existence. And this leads to a really important internal debate within Platonism itself. Are we committed to mathematical objects or mathematical structures?
Right. Let's clarify that distinction. The traditional view, maybe stemming more from Frege, is object Platonism.
Yes, that's the view that the fundamental furniture of the mathematical realm consists of distinct individual items, objects. Things like the number 3, the empty set, maybe the complex number 1. These are seen as individual entities that have identity conditions, you can refer to them, and they are the things our variables range over.
Okay, that feels intuitive, maybe. But you said QPIA, with its focus on quantification, maybe lends itself better to a different view. Structure Platonism, or you called it anti-REM structuralism.
Right. Anti-REM meaning roughly structure before things.
Mm.
Many philosophers, especially those influenced by QPIA in modern mathematics, argue that the true subject matter of mathematics isn't really individual objects considered in isolation, but rather structures.
What is a structure in this philosophical sense?
Stuart Shapiro, a leading proponent, defines a structure as, let me get this right, the abstract form of a system, highlighting the interrelationships among objects and ignoring any features of them that do not affect how they relate to other objects in the system.
Okay. Abstract form. Interrelationships. That's still quite abstract itself. Can we make that more concrete?
Let's try. Think about the structure of the natural numbers with the less than relation. What matters isn't what the numbers are made of, intrinsically. What matters is that there's a first element, 0 or 1, depending on your system. Each element has a unique successor. Every element except the first has a unique predecessor, and so on. It's the pattern of relations that defines the structure.
So the structure is the relational network itself, kind of lifted off from any specific things that might have that network.
That's a good way to put it. It's the abstract pattern. And this leads to a key idea, particularly from Michael Resnick. He argues that individual mathematical entities, like the number 1 or the complex number 1 plus 2i, aren't really objects in the traditional sense. They are merely positions or places within a larger structure.
Positions in a structure, like placeholders.
Exactly. They don't have any intrinsic properties, any stuff they're made of, apart from the properties they inherit from their place in the structure. Their only properties are structural properties, how they relate to the other positions in that specific structure.
Okay, this is where that baseball analogy comes in handy, right?
Yeah.
Let's walk through that again because it really helped me grasp the difference between an object and a position.
Sure thing. Imagine a baseball defense lineup. That defensive setup is a structure. It's defined by 9 specific positions: pitcher, catcher, first base, second base, shortstop, and so on.
Okay.
Now, think about the shortstop position. What is that position? It's a place in the structure. Its defining properties are purely relational, purely structural. It's located between second and third base. It typically fields ground balls hit to that area. It has certain responsibilities like covering second base on a steal attempt, etc.
Right. The position itself doesn't have properties like height or weight or batting average.
Exactly. Those are properties of the concrete object, the actual person, who happens to be playing shortstop at that moment. Let's say it's some player named Alex. Alex, the person, has height, weight, shoe size, a personal history, favorite foods, all sorts of intrinsic properties.
Okay.
But if Alex gets traded or retires or gets injured, does the shortstop position vanish?
No, of course not. The position is still there in the structure of the baseball defense, waiting for the next player to occupy it.
Precisely. The position itself is abstract, defined by its role in the structure, and it persists independently of who occupies it.
So the structural Platonist says the number 2 is like the shortstop position.
That's the analogy. The number 2, for a structuralist, doesn't have some hidden internal constitution. Its identity is its place in the natural number structure. It's the thing that comes after 1 and before 3. It's the result of adding 1 and 1. It's the smallest prime number. All its properties are defined by its relationships to other positions within that structure.
And there are different structures, like the natural number structure, the real number structure, the structure of a geometric space.
Exactly. The claim of anti-REM structuralism, the structure before things, version, is that the entire reality described by mathematics is a vast collection of these abstract, independent, universal structures.
And this is still considered Platonism. It meets the 3 criteria.
Yes, crucially it does. These structures are argued to exist. That's what QPIA commences to. They're abstract, they're clearly non-spatiotemporal and acausal. The shortstop position isn't anywhere specific and doesn't cause anything.
Right.
And they are independent. The structure of the natural numbers, they argue, exists regardless of whether anyone thinks about it.
So structuralism isn't an alternative to Platonism, but rather a specific version of it, defining the kind of abstract stuff that exists.
Exactly.
Yeah.
It's an attempt to articulate the content of the Platonic realm in a way that perhaps better aligns with modern mathematics, which is often explicitly about studying structures like groups, rings, fields, topological spaces, and maybe handles some philosophical problems more neatly than object Platonism.
Okay, so we've built up this impressive edifice. Platonism, whether object-based or structure-based, asserting the existence of an abstract, independent mathematical realm, backed by powerful arguments from language and science. It seems coherent, maybe even necessary. But now we pivot to the elephant in the room, the big challenge.
The reckoning.
By affirming existence, abstractness, especially that critical feature, acausality, and independence, Platonism seems to inadvertently dig a massive ditch around the mathematical realm. A ditch our sources call the impenetrable metaphysical gap.
That's a great way to phrase it. And this gap is almost entirely a consequence of that one feature we keep coming back to, acausality.
Why is acausality the culprit?
Because we, human beings, trying to understand mathematics, we are concrete, spatiotemporal creatures. We live and learn and think firmly within the causal web of the universe. We gain knowledge about the world around us through causal interactions, light photons hitting our retinas, sound waves vibrating our eardrums, physical objects resisting our touch.
Right. Our knowledge seems rooted in cause and effect.
But the abstract mathematical realm, as defined by Platonism, is causally inert. It's completely isolated from this causal web. It can't send us signals. We can't poke it to see what happens.
So we're sitting here in the causal world,
Yep.
and the entire realm of mathematics is sitting over there in the causal world, completely disconnected.
That's the picture Platonism paints.
Yes.
And the immediate devastating question is, how on earth do we bridge that gap? How can we possibly know anything reliable about a realm that we have zero causal contact with?
This is the famous epistemological challenge to Platonism, isn't it? The problem of knowledge.
It is. And it's often considered the most serious objection. It's fundamentally an explanatory demand. Platonists, tell us, how can we, human beings stuck in the causal spatiotemporal world, possibly form justified true beliefs about this completely separate, causal, non-spatiotemporal realm?
It's not just that we have mathematical beliefs, but how could those beliefs possibly be accurate or justified if there's no connection?
Precisely. The mystery isn't just that we have mathematical thoughts. The mystery is why our mathematical beliefs seem to be systematically non-accidentally true about the Platonic realm. If there's no causal pipeline carrying information from that realm to our brains, why should our beliefs reliably track the truths over there?
It seems like any alignment would have to be a massive coincidence, or maybe some kind of mysterious intuition. A mathematical sense.
People have suggested things like that, a special faculty of mathematical intuition. Yeah. But then the challenge just shifts.
Yeah.
How do you justify that intuition? How does this mysterious faculty work without causal interaction? It pushes the explanatory burden back without really solving it.
Okay, let's use that Londoner analogy from the sources again. It really drives home the need for a causal explanation.
Right. So imagine a huge complex event is happening. Say, the U.S. president is giving the State of the Union address in Washington, D.C., full of specific details, policy announcements, turns of phrase.
Okay.
And you are sitting in London. You're completely cut off. No internet, no TV, no radio, no phone, no spies relaying information. You desperately want to know exactly what was said in that speech.
Right.
Now, someone walks up to you in London and claims they know, word for word, the entire content of that complex speech delivered thousands of miles away. And you can verify they have absolutely no causal link, no technological device, no secret notes, no prior briefing.
My immediate reaction would be disbelief. I'd assume they were guessing, making it up, or maybe delusional. I certainly wouldn't count their claim as justified knowledge.
Exactly. And why not?
Why?
The disbelief.
Because there's no plausible story, no mechanism to explain how that incredibly specific, complex information could have traveled from the source, Washington, to the recipient, the person in London, without any causal connection.
Precisely. We intuitively understand that acquiring justified knowledge about complex contingent facts about the external world requires some kind of causal pathway, direct or indirect. Information needs to flow.
And the analogy applies to math because
the Platonic mathematical realm is like Washington, D.C., in that analogy, a source of complex, specific truths. And our minds are like the person in London causally isolated from that source. Platonism, by insisting on acausality, seemed to deliberately cut the only kind of wire, the causal connection, that could plausibly explain how information gets from the mathematical realm to our beliefs.
So without a causal link, Platonism struggles to explain why our mathematical theories aren't just, well, an unbelievable stroke of luck that happens to match the facts in this inaccessible realm.
That's the heart of it. The epistemological challenge boils down to this fundamental question for Platonists. Can you provide a plausible, non-magical explanation for the reliability of our mathematical beliefs about your proposed abstract realm without invoking causal interaction? If they can't, Yeah. The whole position looks shaky, no matter how intuitive it feels or how well QPIA seems to work.
It's a huge hurdle. And that's not the only problem stemming from this causal gap, is it? There's a related challenge concerning meaning and reference.
Yes, the referential challenge.
Yeah.
If we can't causally interact with mathematical entities, how do our words like to or set or pi manage to successfully hook onto or refer determinately to specific entities in that abstract realm?
How does reference normally work?
Well, for concrete objects in the world around us, causal interaction often plays a key role in fixing reference. Think about naming a star. An astronomer points a telescope, a causal device gathering light, observes a specific point of light, and says, let's call that Alpha Centauri. The historical chain of causal interaction with the light from that specific star helps to fix the reference of the name.
Okay. My use of the name traces back to an initial dubbing linked causally to the object.
Right. But what about the number 2? It's a causal. There's no initial dubbing ceremony where someone causally interacted with the abstract number 2 and named it. So how does the word 2 manage to latch onto that specific abstract entity and not some other one or nothing at all?
This feels slippery. How is this problem sharpened? The sources mention structural equivalences.
Exactly. The problem gets really acute when we consider that mathematical domains often have symmetries or structural equivalences. This brings us to the permutation problem. Many mathematical structures possess what are called non-trivial automorphisms. An automorphism is basically a way to shuffle the elements of the structure around, while perfectly preserving all the important structural relationships.
Can you give an example?
Sure. Think about the structure of the integers, mod 2, 1, 1, 0, 1, 2.
Yeah.
Under the operation of addition. Let's call this structure z plus more. Now consider a mapping where you swap every integer in with its negative n. So 1 goes to the -1, -1 goes to 1, 2 goes to -2, -2 goes to 2, 0 stays at 0, and so on.
Okay, like reflecting everything across 0 on the number line.
Right. Now, does this shuffling preserve the structure of addition? Let's check. We know in the original structure that 2 plus 3 equals 5.
Yes.
What happens after the swap? 2 maps to -2, 3 maps to -3, and 5 maps to -5. Is it true in the swap structure that -2 plus -3 for lattice 5?
Yes, it is.
It works perfectly. The entire structure of addition remains unchanged by this permutation. The mapping is an automorphism of z plus Goa.
Okay, I see the symmetry, but how does that create a referential problem?
Well, think about the Platonist who believes the integers exist as abstract objects, independent of us. When they use the singular term 2, which object are they referring to? Is it the entity we normally think of as positive 2? Or could it actually be referring to the entity we normally call negative 2?
But why would it refer to -2?
Because the structure is identical. If the Platonic realm is defined purely by its abstract structure, and the positive 2 position and the negative 2 position are structurally symmetrical under addition via this automorphism, what mechanism in the absence of any causal pointing or dubbing ceremony determines that our term 2 picks out the one we intend rather than the other?
Without causation, there's nothing external to the structure to pin down the reference to one specific position versus its structurally identical twin.
That's the worry. It suggests our reference might be indeterminate between structurally equivalent positions. Our term 2 might not uniquely refer. And if our terms don't uniquely refer, how can our mathematical statements have determinate truth values?
That seems bad. And it gets even worse with more complex mathematics. This leads to the Lowenheim-Skolem problem. You said this was technical, but really significant.
Yes, it's a profound result from mathematical logic, specifically model theory. The Lowenheim-Skolem theorem, well, there are versions of it, but the relevant one here, the downward version, says something quite shocking. It says that any theory expressed in standard first-order logic that has any infinite model at all.
Like a theory describing the real numbers, which are infinite.
Exactly. If such a theory has an infinite model, meaning there's a structure that makes the theory true, then it must also have a model whose domain is countable, even if the theory was intended to describe an uncountable structure.
Wait, hang on. Let me process that. You're saying that a theory like the theory of real numbers, which we think uniquely describes the uncountable continuum,
Yes.
can actually be satisfied, made true, by a structure that only contains a countable number of elements, like as many elements as the natural numbers 1, 2, 3.
That's what the theorem proves, provided the theory is expressed in first-order logic, which is the standard logic used for foundations. The axioms of real analysis or complex analysis or set theory, when written in first-order logic, simply cannot force all their models to be uncountable. They will always admit strange, unexpected countable models that still satisfy all the axioms.
But that seems fundamentally wrong. The very idea of the real numbers seems to depend on them being uncountable. That's crucial for calculus, for measuring lengths, for everything.
It is absolutely central to our intuitive understanding and the standard interpretation. But the logical result is inescapable. First-order logic is just not strong enough to pin down uncountability uniquely.
So how does this create a referential crisis for the Platonist?
Well, the Platonist believes there is this unique, abstract, independent structure out there, the real numbers, which is genuinely uncountable. That's the intended target of their reference when they talk about real analysis.
Right.
But the Löwenheim-Skolem theorem shows that the theory they use, the set of axioms written in logic, doesn't uniquely pick out that intended uncountable structure. The theory is also true of some weird countable structure. So the question becomes, how can the Platonists justify the claim that their term real number successfully refers to the intended uncountable Platonic structure and not to one of these unintended countable structures that also satisfies all the same first-order logical truths?
Again, without causation to somehow link our minds or language to the real uncountable thing.
What fixes the reference? What guarantees our theory is actually about the thing we think it's about? The threat isn't just ambiguity, like with the permutation problem. The threat here is that our entire mathematical language might be systematically failing to refer to the intended Platonic reality. We might think we're talking about the vast ocean of the continuum, when our logical net is only capable of catching a countable bucketful, metaphorically speaking.
Wow, okay. The epistemological challenge asks how we know anything, and the referential challenge asks how our words even connect to anything specific, both stemming from that a causal gap.
That's a powerful critique. The combined force of these challenges, the epistemological gap, the referential indeterminacy, it feels overwhelming. It's really no surprise that philosophers who want to hang on to mathematical realism have had to come up with some equally radical responses.
Absolutely. You can't face challenges that deep with minor tweaks. You need big ideas.
And arguably the most ambitious, maybe the most counterintuitive response from within Platonism itself is this thing called full-blooded Platonism, or FBP.
Yes, FBP, which is strongly associated with philosophers like Mark Balaguer and perhaps Stuart Shapiro in some reading. It takes a really bold approach. Instead of trying to bridge or close that metaphysical gap created by acausality,
What does it do?
it basically tries to make the gap irrelevant. It concedes the gap exists, concedes we have no causal contact, but argues that it doesn't matter for knowledge or reference.
How on earth does it manage that? It does it by proposing a radically maximalist view of what the abstract mathematical realm is like. FBP rests on two core theses.
Okay, thesis A.
Thesis A is plenitude. This is the idea that the mathematical realm isn't just big, it's maximally big. It is absolutely jam-packed. It contains objects and structures related in all logically possible, consistent ways.
All possible ways. What does that mean?
It means that if you can come up with a mathematical theory, any set of axioms and rules that is logically consistent, meaning it doesn't lead to a contradiction like P and not P, then plenitude guarantees that somewhere in the vast Platonic universe there exists a structure that perfectly models that theory, makes it true.
So if my theory is just consistent, then it's automatically true of something in the Platonic realm.
That's the claim of plenitude. The realm is so incredibly rich, so full-blooded, that consistency is sufficient for existence. If it's possible, it exists somewhere in the mathematical universe.
Wow. Okay. That's a huge metaphysical assumption. What's thesis B?
Thesis B is schematic reference, and this tackles the referential challenges head-on. FBP argues that the whole worry about permutation problems in Löwenheim-Skolem is based on a mistake applying the wrong model of reference to mathematics.
What's the wrong model?
The model of non-schematic specific reference that we use for concrete objects, like needing Alpha Centauri to pick out that specific star and no other.
Okay. So what's the right model for math, according to FBP?
FBP says mathematical reference is purely schematic. When mathematicians develop a theory, like group theory or topology, they aren't intending to refer to one single, unique Platonic structure out there. Instead, the theory functions like a blueprint or a schema. It refers schematically to any structure, any part of the Platonic realm that happens to satisfy the constraints laid out by the theory's axioms.
So it's more like saying, I'm talking about anything that fits this description.
Exactly. It's modeled on the logician's concept of truth in a model. A theory is true of a model if the model satisfies the theory's axioms. FBP says that's all mathematical reference is. The theory places constraints, and it successfully refers if something in the plenitudinous realm meets those constraints. Which specific thing it is doesn't matter.
I see how this tackles the reference problems now, if reference is schematic.
Then the permutation problem dissolves. It doesn't matter if the term 2 could refer to positive 2 or negative 2 under addition, because both interpretations satisfy the structural constraints of the theory Z plus. The schematic reference succeeds either way.
And Lowenheim's golem.
Same thing. It doesn't matter if the first-order theory of real numbers is satisfied by an uncountable structure and a countable one. As long as a structure exists that satisfies the axioms, which plenitude guarantees, assuming the theory is consistent, the schematic reference is successful. The theory is true of those structures that fit.
That's clever. It sidesteps the uniqueness problem by denying that uniqueness was ever the goal. But how does FBP handle the epistemological challenge? How do we gain knowledge if there's no causal contact and reference is just schematic?
This is where the plenitude thesis does the heavy lifting again. Remember, plenitude says any consistent mathematical theory corresponds to some existing structure in the realm.
Right.
So according to FBP, how do we acquire mathematical knowledge? We don't need mysterious causal links or special intuition faculties beaming information from the Platonic realm. All we need to do is acquire knowledge that a particular mathematical theory is logically consistent.
And consistency. That's something we investigate here in the causal world, right? Through logic, proof, trying to derive contradictions.
Exactly. Determining consistency is a standard, quasi-empirical, rational activity that mathematicians engage in all the time. We do it through proof, model building, logical analysis, all activities grounded in this world.
So if I can rigorously demonstrate through proof methods available to me that my theory of, say, widgets is logically consistent,
then FDP says you have thereby gained knowledge. Because the plenitude principle guarantees that since your widget theory is consistent, there must be a part of the Platonic realm where widget structures exist and make your theory true. Your knowledge is knowledge that such a truth maker exists, guaranteed by consistency.
Wow. It completely reframes the epistemological task. It's not about somehow seeing into the abstract realm. It's about proving consistency here and now.
It's a really ingenious, if metaphysically extravagant solution. It tries to solve the epistemological and referential problems by essentially inflating the ontology to the maximum possible extent.
Okay, FBP is one powerful response from within Platonism. But surely not everyone buys into that level of metaphysical plenitude. What about philosophers who still want mathematical realism? They believe math entities exist and are objective, but they just can't swallow all three of the classical Platonist theses: existence, abstractness, independence.
Right. These are the non-Platonist realists. They hang on to existence. They usually want objectivity, which often relates to independence, and they need mathematical terms to have semantic values, reference, for math to be true.
Yeah.
But they typically find fault with the strong versions of either the abstractness thesis, especially causality and necessity, or the independence thesis.
Okay, let's look at those who challenge abstractness first, maybe under the banner of Quinian realism or anti-nominalism.
Yes. Remember Quine's indispensability argument, QPIA.
Yeah.
It commits us to mathematical entities because they're indispensable to science.
Right. Science needs them, so they exist.
But Quine, and philosophers following him, treat mathematical knowledge as being fundamentally on par with empirical scientific knowledge. It's part of the same web of belief. It's not some special a priori knowledge completely separate from experience. So, if mathematical entities are posits justified by their role in science, just like theoretical entities like electrons or quarks are, then why should we saddle mathematical entities with all that extra metaphysical baggage of the traditional abstractness thesis, causality, eternality, changelessness, necessity?
You mean maybe numbers are more like electrons than like Platonic forms?
That's the direction some thinkers go.
Mm.
Maybe the distinction between abstract and concrete isn't as sharp or as important as traditional philosophy thought. Michael Resnick, for instance, argued that based on scientific practice, the distinction might not even be meaningfully drawn. So they accept the existence of mathematical entities via QPIA, but they reject or remain agnostic about the traditional abstractness thesis.
So it's a kind of minimalist realism. Believe they exist because science needs them, but don't speculate too much about their ultimate metaphysical nature beyond that.
Exactly. Philosophers like John Burgess identify with anti-nominalism. They strongly oppose nominalism, the view that mathematical entities don't exist. They accept the ontological commitment derived from QPIA, but they refuse to go further and make strong metaphysical claims about whether these entities are causal or necessary or eternal, arguing that science doesn't really give us grounds to make those extra claims.
And how does this help with the epistemological challenge?
Well, if you drop the strict acausality part of abstractness, the challenge loses much of its bite. If mathematical entities are more like electrons, perhaps we gain knowledge of them through their role in the causal empirical world via their explanatory function in science. The impenetrable gap starts to look, well, penetrable if you remove the acausality assumption.
Okay, so that's one way out. Keep existence, keep objectivity, derived from science, but question abstractness necessity. What's the other major non-Platonist route? Rejecting independence.
Yes. This leads to various forms of metaphysical constructivism. Constructivists are often realists in the sense that they accept mathematical entities exist and maybe even that they are abstract in some sense, not physical objects, but they fundamentally reject the independence thesis.
They deny that math would exist without us.
Essentially, yes. They argue that mathematical entities, while real and objective in some way, are ultimately dependent on human rational activities, our minds, our language, our social practices. They are constructed, not discovered, in a pre-existing Platonic realm.
So this brings math down from the heavens, so to speak, and makes it a human creation.
In a sense, but different constructivists locate the construction differently. For someone like L.E.J. Brouwer or Aaron Hading intuitionists, mathematical entities were primarily mental constructions, built up by an idealized mathematical subject following specific constructive rules.
Okay, so math exists in the idealized mind.
Others, like Paul Ernest, see mathematics as arising from human linguistic activities and social agreement. The rules and objects are products of our language games and conventions.
More social.
And then there's a view, pushed by philosophers like Reuben Hirsch and perhaps Julian Cole, that sees mathematical entities as social institutional entities.
Social institutional, like what?
Like the U.S. Supreme Court or the rules of chess or maybe a corporation like Greenpeace. These things clearly exist. They have structure, rules, objective properties within their system. They exert influence.
Right. The Supreme Court is real. It makes binding decisions. But it obviously wouldn't exist without human society, laws, appointments, etc. It's dependent.
Exactly. So the social institutional constructivist says mathematical objects and structures are like that. The number system, Euclidean geometry, set theory, these are vast, complex, objective institutional structures created and sustained by the collective activity of the mathematical community over centuries.
So 2 plus 2 plus 4 is objective and true, but its truth and the existence of 2 and 4 are grounded in the human-created institution of arithmetic, not in an independent Platonic realm.
That's the core idea. This view provides a very clear answer to the epistemological challenge. We know about mathematical entities because we built them. We have access to the rules and structures because they are products of our own collective rational activities.
And reference.
Reference is also less problematic. Our term 2 refers to the specific element defined within our socially constructed system of arithmetic. There's no gap to bridge to an independent realm.
But does it preserve the sense of objectivity and necessity that feels so strong in mathematics?
That's the main challenge for constructivism. Can a human construction really have the kind of necessity and universal applicability that mathematical truths seem to possess? Constructivists argue that the objectivity comes from the rigor and stability of the institution itself. But critics often feel it makes math too contingent on human practices.
Okay, what a journey. We started with a seemingly simple question. Does the number 7 exist like a star? And we found that mathematical Platonism offers this incredibly sophisticated, demanding yes. It says, yes, it exists, but in this utterly unique way as an abstract, a causal, non-spatio-temporal, independent entity.
And we saw how this view isn't just asserted, but systematically defended. First through Frege's analysis of how we use language about numbers, and then, more broadly, through the powerful Quine-Putnam argument that math is simply indispensable for our best science.
But then the twist. The very features that make Platonism seem right, the abstractness, the independence, they carve out that deep metaphysical gap. The gap that leaves us wondering how we could possibly know anything about this causal realm.
That's the epistemological challenge.
And how our words could possibly hook onto specific entities within it, given the problems of permutation and logical limitations like Lowenheim's golem.
The referential challenge,
yeah.
These challenges are so profound that they really shape the entire landscape of modern philosophy of mathematics.
We saw how Platonists might respond with something as radical as full-blooded Platonism, essentially saying the realm is so full that consistency guarantees existence, making the gap irrelevant.
A bold move, solving the access problem by making the reality incredibly abundant in our reference schematic.
Or how other realists try to keep the existence and objectivity of math but are forced to abandon traditional Platonism. They might question the strong claims of abstractness, treating math entities more like scientific posits.
The Quinian or anti-nominalist route.
Or they reject independence altogether, grounding mathematics in human construction, whether mental, linguistic, or social institutional.
The constructivist route.
Yeah.
Every position seems to involve trading off certain intuitions.
It really highlights the core tension, doesn't it? We have these incredibly successful, objective, seemingly necessary mathematical theories that form the language of science itself. But if we take the most straightforward explanation that they describe a real independent Platonic realm, then our ability to access or even refer to that realm becomes deeply, deeply mysterious.
That tension is palpable. The objectivity pulls us towards Platonism. The epistemology pushes us away. Every view we've looked at today is really an attempt to find a stable way to reconcile that profound conflict between the nature of mathematical truth and the nature of human knowledge.
And that ongoing tension, particularly the response offered by full-blooded Platonism, leaves us with a really provocative final thought, something for you, the listener, to perhaps mull over. FBP suggests the abstract mathematical realm is almost infinitely bountiful. It contains a reality corresponding to any logically consistent theory.
If it's consistent, it exists there.
So, if that's true, if mathematical reality contains all consistent possibilities already laid out, then what is the mathematician actually doing when they prove a new theorem? Are they genuinely discovering a unique, preordained truth about the fundamental structure of reality? Or are they perhaps more like inventors, merely mapping out and exploring one particular self-chosen corner of an infinite, ready-made metaphysical warehouse full of countless other equally valid, equally real mathematical structures that just happen to be consistent? What does discovery mean in a realm of infinite plenitude?